Alright, so now that we have the basis and the rationale for why hybrid orbital or hybridization of atomic orbitals is valuable for helping us describe real molecular geometries or experimental molecular geometries, let's do some examples and let's just walk through step by step. So we're going to start with this example. It says identify the orbitals that overlap to form the PCl bonds in the PCl3 molecule. So we're going to walk through this step by step, starting with step. We'll start by drawing the electron dot structure of PCl3, which will give us a sense for what the two-dimensional structure are, where the bonds are, and then from there we'll go to 3D. So pause the video here and see if you can draw the same structure that I'm going to draw. So I counted 26 valence electrons on the entire molecule. 6 of those were used to form the first bond's connectivity with phosphorus in the middle. I then distributed 18 electrons across the chlorine peripheral atoms to fill their octets. That left me 2 extras. Those 2 then are the red ones that show up on the central phosphorus atom. So from here we can identify that there are 4 charge clouds on the central atom of phosphorus. So what would the molecular shape of this be if we had 4 charge clouds and 3 bonds? This will be a trigonal pyramidal shape. So let's store this for now. Let's go on to step. And let's write the electron configuration for the chlorine atom in PCl3. So pause the video and make sure you can write that out. So chlorine is in group 7A, so we could write that as the closed shell structure, neon, 2s2, 2p5. We know that that should have 7 valence electrons, which it does. I could write this more explicitly, which will help me in just thinking about the bonding, as closed shell 2s2, 2pz2, 2py2, and 2px2. And again, whatever I choose here, x, y, z, it doesn't matter. It doesn't matter at all. It'll matter when I draw the ultimate molecule, which one I chose here. I want to be self-consistent, but I could have easily written this as 2px2, 2pz2, and 2py1. It doesn't matter in this case. It's an arbitrary choice. What's important here, though, is to note that this 2px here is where we have 1 unpaired electron where we could form a bond to that chlorine atom. So let's write the valence electron configuration for the central atom phosphorus in this case. Okay, so phosphorus is in group 5, which we know that means it has a valence shell of 5 electrons. We could write that out as neon 2s2, 2p3, or be explicit, and we could write this out as neon 2s2, 2px1, 2py1, 2pz1. Again, doesn't matter how you order these. In this case, it doesn't matter because they each have 1, but it wouldn't matter anyway. We just need to be self-consistent later when we actually draw the structure. So the 4th step is to think about shape way over here, which we've already started to do. So we know that there are 4 charge clouds from our Lewis structure. We identified those as 1, 2, 3 of the single bonds, and then 4 to count the lone pair. And there are 3 bonds that form here. And so in this case, we would have, since we have 4 charge clouds, we would need a hybridization in terms of the shape of this thing that would have 4 essentially equivalent orbitals. So if you've got 4 charge clouds here, then we need 4 equivalent orbitals on the central atom to make these bonds all the same. If we look down at our electron configuration for phosphorus, we have 3 orbitals that are equivalent, but we don't have 4. We have the other excess electrons. Those would be hanging out in our 2s2 orbital, so they're not equivalent. So hybridization is always going to be how many charge clouds you have. So if you have 4 charge clouds, if you need to have 4 charge clouds, then that means you need 4 equivalent orbitals. How do you get 4 equivalent orbitals? Well, you hybridize the you hybridize the s and the p's, all 4 of them, to give you 4 new hybrids, which we'd already called the sp3 orbitals. Okay, so now that we've identified that we have these 4 charge clouds, which means we need 4 equivalent orbitals, which means we're going to hybridize all of the 4 atomic orbitals in the valence set, the 2s and the 2p's, all 3 of those. So we'll have 4 new sp3 hybrids, or 2 sp3 hybrids, we should say, to be clear. The 2 meaning that's coming from the principal quantum number 2, not that we have 2 of them, because we actually have 4 of them. Now we can draw this. So we can say that phosphorus is our central atom, and if we've hybridized 4 of these, remember the hybridization is going to look like this. So we've got a 2s, and then we've got our 2p's, and we're going to mash all those together, right, and average them, and that's going to give us these 1, 2, 3, 4, these 2 sp3 orbitals, all 4 of them. And let's see, we can fill those with what we had to start with in our central atom, because remember this hybridization here, this is for the p atom. This is for the central atom. We're not talking about chlorine at all. Chlorine is going to stay as it is. We don't need to hybridize that because the molecular geometry doesn't depend on chlorine's orbitals. It only depends on the central phosphorus atom. So we've got all of these electrons, 5 of them, that were originally in the unhybridized set. So it would look like this. Once we hybridize that, we still have the same number of electrons. So we have 1, 2, 3, 4, 5 here, which means we still have these 3 unpaired electrons to form our bonds with that unpaired electron from the 2px orbital of chlorine. So I'm going to move this up a little bit and draw our phosphorus here. I'll draw it, and then I'll show you a computer picture of it so that it does a better justice for that. So we'll start by drawing out these sp3 orbitals, right? They're all equivalent, so they're going to look just like they did for the tetrahedral methane molecule. So we'll have sort of one poking up like this. Remember, they look like these. The sp3 orbital looks like this. It's got like this big side of the dumbbell and the small side of the dumbbell, so it's going to look like that. I probably won't draw the small side of the dumbbell just because it's going to make it look complicated. We would have one poking out over here. All of these 3 would be in the plane. We'd have one coming out of the plane, so maybe I'll bold this side to make it look like it's a wedge. So it's coming out of the plane, and then we'd have one coming back here, and I'll dot that one because that's the one that's going in the back of the plane. So these green here are the sp3 orbitals, the 2 sp3 orbitals to be specific. Each one of those is going to have, well, 3 of them here are going to have a lone pair. So there's going to be one there, an electron there, an electron there. I'll draw those electrons in. And then here we'll have 2 in that one, coming from our energy diagram, right? And so we've got 3 of these chlorines, all with their 2px orbitals here. So I'm going to take chlorine, and I'm going to draw that in, say here, and I'll draw a chlorine here, and a chlorine here, and then I'll draw its px orbital. So this px orbital is going to look like that, px orbital is going to look like that, px orbitals look like that. I'm just overlapping that one phase, and then I'll draw the other side of the p orbital, which would look like this, this, and this. So this is the final structure of our PCl3. The question from the beginning, remember, was describe the bond, the PCl bond. And now we can say the PCl bond is formed between a 2sp3 hybrid orbital on phosphorus, and that's bound to a 2px orbital on Cl. That's what this bond is made of. And the geometry, we already knew the geometry was going to be trigonal pyramidal, but it's represented here three-dimensionally. So I'm going to pause the video and then I'm going to paste in what this would look like, maybe in a clearer picture. Okay, so this shows a picture from a textbook. So you've got the 4 phosphorus 2 sp3 orbitals, all arranged at 109.5 degrees relative to each other tetrahedrally, and you can see the black dots represent all of those electrons that were placed. So we had our 2s and our 2p, and remember there were total of 5 electrons actually to start with. Once those were hybridized into 4 equivalent orbitals, we smashed those in like this, and these were the sp3s. So these two became the lone pair, and these 3 became the 3 that will eventually form the bonds between the chlorine. So chlorine then has 1 lone pair from its 2px, and those come in and overlap as such, and they give you a structure which I would say is not terribly different from the one I drew. You have to admit I'm doing this all by hand on a computer, so yeah, they're not terribly different from each other, but this gives you a better sense for what this would look like realistically, and it gives you a better sense that the bond, the PCl bond, is actually formed between the 2p orbital of chlorine and the 2sp3 orbital of the phosphorus, and we end up having 3 of those bonds.